Welcome to the Machine Learning at Home. Today I will speak about distances. We already understand what distances are in general because we already use two methods related to them. So DNN and also k-means are both methods which use distances. A bit hiddenly, but there are distances which participate in understanding which of data point is closer to which one. So let me speak about distances a bit more. It's a wonderful method because it will allow us to get rid of all these diverse characters and go from multidimensional space to the very special and straightforward space of distances. Operation of distances is very straightforward as well, and understanding of distances is also easy enough. However, working with distances will come with a price. So first of all, if you, for example, have like 10 objects to work with, then to add 11th object to them, you will need to go back to the initial matrix and calculate distance with 11 objects. So it's impossible to add 11th object directly to the distance matrix. And a second problem which is associated with distances is that distances are keeping in kind of background that your data should be metric, measurement data, consist of numbers. So this is why the most widespread methods of calculation distances is Euclidean, geometric distance. So there are, however, much more distances which you might apply to your data, and I will speak about universal distances or universal metrics. So let me show you how they work. So first of all, we create the new iris data by simply copying the initial iris into the new name. And then I will modify iris2 in character number 4, which is the petal width, and will make it cut with 3 intervals. So I will use a previous dataset character number 4, cut it into 3 intervals, and logically the first part of the interval will be most narrow petals, then it will be medium-sized, medium-width petals, and the last part will be broad petals. So labels will be supplied to tell about it. So I need 3 labels, so I put 6 quotes and then I put commas between them, and then I will enter names of labels. So it will be narrow, medium, and broad petals. Okay, so this is how our data set will now be organized, and if we check it with str, you will see that the petal width now is a factor with 3 levels: narrow, medium, and broad, logically. So now if we apply any distance, default distance, to that data, R will likely give us a warning, because it by default does not work well with this type of information, factor, which are in essence categorical data. So let me show how to work with them. You will need a library which is by default installed with R. Library cluster. And that library, again, you doesn't need to install it, so it should be present by default. And that library consists of multiple functions. One of important function is DAISY, which is able to calculate so-called universal goer distance. So let me show how it works. Iris2, we don't need species for that calculation. As usual, we'll take it out. But we will need first 4 characters, including our new petal width, which is in essence categorical character now. And we should specify metric, which is gover. And of course we should save it in some object like iris.d, for example. Okay, and this is it. So no warnings, everything went without problems. So how now to work with this new distance? For example, there are methods similar to k-means which however use any distances. So by default, k-means itself use Euclidean geometric distance for our iris2 data is not applicable. But if we use so-called partitioning around medoids or PAM, we can use our new data iris2 and our new distance iris.d. So let me show how to make it. We called the new object iris PAM and use function PAM. Again, this is partitioning around medoids. So k-means like method, which however uses any distances, including distances we just obtained from the gover universal metric. So we use it iris.d. And then, as usual, as for k-means, we must provide the desired number of clusters. In that case, option is called key equal to 3, because we want 3 species. This is, by the way, characteristic of all k-means like methods. They want to tell how many clusters we want from them. Okay. And then we need to compare what is going on. Did it find the proper species or not? Of course, as you see here, PAM didn't know anything about species. It's only new distances. Only distances, nothing else. So let us see how it works. For that check-in, I will need to load my library Shipunov, and then I will use my mis class uppercase function and compare our iris PAM, the information about clusters contained in the object clustering. Okay, and our initial species are iris, of course, column number 5. And I will need to say best equal to true, because PAM doesn't know species names, so it will give these species like classes numbers, not names. So to compare numbers with species names, we need option best equal to true. Wonderful. This method works even better than default k-means. As you see, it gives 3 numbers for like proposed species, but these numbers corresponding very well with the species name. So number 1 corresponds with setosa, and all 50 setosas went to that number, to that class. 49 of versicolor went to the class number 2, and 45 of virginica went to the class number 3. So the most specific it was for setosa and versicolor. For virginica less specific. So this is very good results, taking into account that methods doesn't know anything about classes. Now, like next variant of machine learning is proper machine learning with training group, and typically DNN uses distances. So it uses them implicitly somewhere inside, and it typically uses only Euclidean distances. So how to use our gover distance? This is a function which I called DNN, or distance-based KNN. Let me show how to work with it. That function is available from my package, so we already loaded it. Let us create training and testing subset because it will be true machine learning. So from iris 2 we need 1 to 5 more than 4. For each fifth row it will be training data. For testing subset we will need the same but with negation, with exclamation mark. Okay, we did it, and now we use that DNN, which is a distance-based KNN. So it has interface similar to KNN. KNN is a lazy classifier. DNN is even, we can call it super lazy classifier because it does not actually calculate anything. The calculation of distance is a different function. So we need to supply DNN with training, testing, classes, and number of neighbors to consider, and finally how we want to calculate the distance. So let us do it. It's a long state. Anyway, so iris DNN will be the name of our final object. The name of function is D uppercase, NN lowercase, and then we'll need same arguments as in KNN. So iris to train without species. Then we need the testing specification, iris to test, again without species. Now we need species from the train, iris to train variable number 5. So far looks like we did everything well. Then we need, so DNN is different from default KNN because it always wants the number of neighbors to be specified, or the distance, but it's a different story. So key equal to 5. And finally, we also need to tell DNN how do we want to calculate our distances. KNN doesn't need it because it always uses Euclidean distance. DNN wants us to specify argument fun uppercase, and that might be a bit difficult to understand from the start because it's what called anonymous function. So kind of thing which will be run every time when we work with training testing data. So we specify it with the keyword function, and argument I typically use .x only for anonymous function. That will be easily seen. If you see .x, that's anonymous function. You can do it any number on any letter if you want. And then what exactly we want? We want to run daisy and run it on this .x, and each time it will run it use metric equal to gover, universal metric. We need universal metric because our character number 4 is not a number. And let me calculate number of brackets properly. One parenthesis open, one close, second parenthesis open, second close. Looks like everything is good. Let us check it simply by running it. Yes, looks like everything is good. And now iris DNN contains names of classes, and we can directly use misclass uppercase function to compare our predicted DNN names of classes with actual names of classes, which are iris to test contains in variable number 5 of iris to test. Alright, let us see. So I would say wonderful results. So it works perfectly well. We actually omitted some information because when we did that cut here, many numerical information was just forgotten. We simply put everything in 3 groups: narrow, medium, broad, and all different numbers were were put in one group. Of course, this group corresponds with lower, medium, and higher values, but still, information was lost. So even with information lost, we only have 3 cases misclassified. I think it's a very good result. So this is how DNN works. So DNN is a distance-based KNN, KNN in which we can change the way of distance calculation. And PAM is a kind of k-means which also allow you to change the distance calculation. So this is how to work with distances if your data contain more or less unusual types of variable. Thank you.